Hello, everybody. This is going to be a quick, well, reasonably quick video on how variance and sample size are related to power. All right. Now, to do this, we're going to frame everything in the context of a simple z-test. Okay. Now, we're going to start off with a basic idea in math and then move on from there. Now, that basic idea helps us understand how variance and sample size can affect power, or how it's related to power. All right. So I'm going to use some visual aids. I'm also going to try and slow down. Very often I speak, especially in my lecture videos, very quickly. Usually when we're digesting content online, I like it to be at a fast pace. So I try to do that, but not in this video. I'm going to try and slow things down, okay? So I'm going to share my screen with you, give you some visual aids, and hopefully that'll help. We'll come back to this in a second. So, again, this video is about how variability in sample size, oh, that's a typo, affect power, okay? So, let's start with a very basic idea, all right? When we have any number over any other number, we have we have a numerator and a denominator, okay? Now, if we divide that out, right, the quotient of that becomes 1, all right? 1 divided by 1 is 1. But what happens if we start changing either of those numbers? First, what happens if we change the bottom number? What if we make it bigger, right? So let's say we change the denominator from 1 to 2. Now, 1 divided by 2 is a smaller number. It's 0.5. So 1 over 2, when the number on the bottom is bigger, the overall quotient is less than when the number on the bottom, the denominator, is smaller. All right, so 1 over 2 is smaller than 1 over 1. So as the denominator grows bigger, the quotient grows smaller. All right. What if we did the opposite, right? What if we left the number on the bottom? What if we left the denominator at 1 and we made the number on top bigger? We made it 2. All right. Well, 2 divided by 1 is 2. So 2 divided by 1 is more than 1 divided by 1, right? 2 divided by 1 is 2. 1 divided by 1 is 1, right? This is hyper simplistic. I know that. But in a bit, this basic concept will help us understand how variation in sample size can affect power, okay? But I wanted to get everybody's mind fixed on this basic feature of semi-simple math, okay? So, again, just to review, when we increase the denominator, the bottom number, the quotient gets smaller. When we increase the numerator, the top number, the quotient gets bigger. All right. Now, how does this apply to the relationship between variance, sample size, and power? Well, like I said, this whole video is going to be in the context of a z-test. So let's look at a z-test formula. There you see it. We have the mean minus the population mean divided by the standard error. Now, let's focus on that top piece, mean minus the population mean, right? So, or an individual number, usually an individual number or sample, minus, or the mean of a sample minus the population mean, all right? What happens when that top piece gets bigger? So what happens when the group or the individual moves further away from the population mean? Well, the number on top gets bigger, all right? And what did we just talk about? As the numerator gets bigger, the quotient gets bigger. So as the difference between the individual or sample mean gets further away from the population mean, that z-test, that z-value gets much bigger, all right? But the bottom number right here, right here is that is that standard error, all right? It's the denominator. Well, we know from what we were talking about before that as the denominator gets bigger, the quotient, in this case, the z-test value, gets smaller. So as the standard error, the bottom piece, grows, the quotient, the z-test value, I skipped the word value there, gets smaller, okay? Now what does this do for our power? How does that affect it? Well, remember, if you go look at another of my videos, power is our ability to see or find an effect, okay? So anything that makes it harder to find an effect lowers our power. Anything that makes it easier to find effect increases our power, because again, power is our ability to find an effect. So with z-testing, t-tests, f-tests, with any test involving a critical value, we're needing a value, in the case of the example we're using here, a z-test value. We need it to meet or exceed some critical value, meaning we need the absolute value to be big, all right? So anything that makes the z-test value or the test statistic bigger increases our power. Anything that makes the test statistic, in our case, the z-test value, smaller reduces it, all right? Because anything that makes the z-test value bigger makes it easier to find an effect. Anything that makes the z-test value smaller makes it harder to find an effect because it's going to be less likely to meet or exceed a critical value. Now, how can variance and sample size make the z-test value bigger or smaller? Well, to figure that out, we've got to look, let's bring our attention right back to the z-test formula, and you see it there. So z equals the mean minus the population mean over the standard error. The bottom number there is standard error. Well, let's look at the formula for standard error, all right? Standard error involves a measure of variance, specifically in this formula, standard deviation, divided by the square root of your sample size of n. Now, because of the basics of the math that we've talked about before, if we change variance, the top number, or change the sample size, the bottom number, we're going to change the size of standard error. And remember what we talked about earlier. Since standard error is the denominator, and because making the denominator bigger makes the quotient smaller, anything that makes the standard error bigger is going to make your z-test value, the quotient, smaller, all right? So how can standard error do that? So let's zoom into standard error. So here is the formula for standard error. We've got standard deviation on top, square root of sample size on bottom. Side note, you notice the side note is off to the side. I'm a dork. Okay, I'm going to be saying things like standard deviation is variance. I want you to understand the distinction between the concept of variance and the statistic variance. Standard error, standard error, standard deviation, and the statistic variance. These are all measures of variance, all right? So standard deviation is a measure of variance. The statistic variance is a measure of variance. Oh, I forgot. But variance is just a concept that refers to how spread out our individual scores are, all right? Now, let's go back to the formula for standard error that we see there. So that top piece, that's standard deviation, variance. That bottom piece is the square root of n. N is our sample size, all right? Now, because of those simple math concepts that we talked about before, at the very beginning, changing variance does something to standard error, and changing our sample size does something to standard error. Let's talk about each of those. We're going to first talk about standard error, standard deviation, variance. Remember back before what we said happens when you increase the top number. When you increase the top number, you increase the quotient size. So if we increased standard deviation here, you see it circled there. If we increase the standard deviation, if we increase the variance in our sample, that's going to make the quotient, standard error, bigger. Okay. Now, what happens when we increase the sample size? Well, again, sample size here is in the bottom. It's the denominator. So yeah, we're going to square root it, and that's going to make it smaller. But the bigger the n, the bigger the square root of n. Okay. Now, remember earlier, when you increase the size of the denominator, you decrease the size of the quotient. So if we increase the sample size, we decrease the standard error. Okay, so again, we increase standard deviation, meaning we increase the numerator, we increase standard error. We increase sample size is the denominator. And when we increase the size of the denominator, we decrease the size of the quotient. In this case, we would decrease the standard error. All right, so more variance, bigger standard error. More sample, more people, bigger sample size, smaller standard error. All right. So what does that mean for our z-test value? Well, let's hold the top piece of our z formula constant, okay? If we increase our standard deviation, right, we said this before, then the top number gets bigger, and as you can see circled here, the quotient, or in this case standard error, gets bigger. This is just repeating what I said before. When the sample size goes up, the bottom number gets bigger, which causes the quotient to get smaller, akin to what we see here. All right. So now let's pull that all together. All right. So again, remember, power just means power is the chances of finding or seeing an effect, right? So as variance, the top piece, the standard deviation, goes up. The top number, the numerator, is getting bigger, meaning the quotient, the standard error, is getting bigger. Okay. The standard error, if we take that standard error, that bigger standard error, and then we plop it back down into the z-test, that means the denominator in that z-test has gotten bigger. Remember that as the denominator gets bigger, the quotient, or now in this case, the z-test value gets smaller. So more variance, greater standard error, smaller z statistic. All right. Smaller z, if we have a smaller z statistic, then we are not going to be as likely to hit one of those critical values or exceed it. That means the chances of us finding an effect are smaller. Therefore, more variance, smaller z-test statistic, less chance of finding an effect. Therefore, greater variance makes it harder for us to find an effect. And anything, as we mentioned before, anything that makes it harder to find an effect reduces power. So variance, greater variance impairs our power. But what about the bottom side of the standard error formula, sample size? Again, remember, power is the chance of seeing or finding an effect. Well, as sample size goes up, right, the denominator of the standard error goes up, then standard error goes down, right? Then we plot that smaller standard error down in the z-test formula. It's the denominator, and it's smaller. Remember what we said before? As the denominator gets smaller, the quotient, in this case the z-test value, gets bigger. So, bigger sample size, smaller standard error. Smaller standard error, bigger z-test. The bigger the z-test, the greater the chances that we'll meet or exceed some critical value, meaning we have a better chance of finding an effect. Remember, anything that increases our chances of finding an effect increases our power. So greater sample size, greater power. All right. I try to go slow, try to lay that all out, and I hope it helped. But that logic applies to every test statistic, even t-test. So I challenge you to try and go through that whole thing on all and that logic for a one sample t-test formula. All right, guys, that is it for this video. I hope I made it clearer rather than more difficult. And like I said in my video over the logic of null hypothesis testing, if I made it worse, ignore this whole video. But I hope I was able to help. All right, guys, that's it for this video. As always, if you have any questions, send them my way. If not, I'll see you around.